Hello everyone, good evening.
Good evening, ma'am.
Yes, so we'll be starting week 3 today. Um, how many of you went through the lectures? Week 2 deadline just yesterday.
Watched some of the lectures, not all.
Some of the lectures, okay. What about others? Did anyone start?
No, ma'am.
Yes, ma'am. I see 3 to 4 lecture.
Okay. All right. So week 3, we are starting a new algorithm, and we'll discuss what the clustering is, and the algorithm that we'll see for clustering is K-means algorithm, or which is also called the Lloyd's algorithm. So week 1, 2, we saw the one unsupervised learning, which is principal component analysis, that we discussed in week 1, 2. And week 3, we're going to discuss another unsupervised learning technique, which is clustering. So we'll see what clustering is. So, like before we start, in general, like what do you understand by a clustering? I mean, clusters.
Putting similar data in a group in clusters.
Yeah, putting similar data in one group is what we can think of clustering as, right? So this is exactly what our problem is today. So, like once we have our data set with us, so there are certain things, like in case there are some grouping in the data set, how do we uncover those structures in the data set, right? So for that, we'll see like how to proceed with certain kind of situations. So what we'll have in general is, we'll have with us is the data set, right? So we'll have x1, x2, let's say till xn. We'll have this data set, and these data set will have some labels associated with it. So maybe I can call the labels as denote this as zi's. Okay. So for x1, maybe the label is 1, and let's say I have only two two clusters. Okay. So I have only two clusters. I want to put this whole data set in just two clusters. So in that case, each of my data point will either go to cluster 1 or it will either go to cluster 2. These are the only two options. So let's say there are some, and we'll denote these cluster indicators by Zi. Okay. So these are the cluster indicator which says Z1 is equal to 1. It means that my data point X1 belongs to cluster 1. C1 here to denote the cluster 1. Let's say if I write Z2 is equal to 1, it means that my data point X2 belongs to cluster 1. All right. Similarly, let's say sum Zi is equal to 2. It means that my data point Xi's belong to cluster 2, right? So this is what we can make sense of from like whenever you see something like this. Okay, this is what it means. So this is what we are trying to do. We are trying to put our data set into specific number of cluster, whatever we have decided. And let's say for k is equal to 2, this is what we looked at. Now, what, like, we can take some very small example to understand this better. So let's say I have just 5 data point, or let's say 4 data point. So I have with me x1, x2, x3, and x4. I have these 4 data points. Now, what I am saying is that we have to cluster this 4 data points, okay? And let's say I want to put them into 2 clusters, all right? So I have just 2 clusters. So one is cluster 1. Okay, so okay. If I'm saying I want to put it in 2 cluster, so what are possibilities we can have? Let's say my first data point was in cluster 1 and the other 3 points are in cluster 2. Let's say x2, x3, x4 are in cluster 2. Or what could happen is that x2 and x4 are in cluster 1 and x1 and x3 are in cluster 2, right? This can happen. And you can have another case where I can say maybe x3 is in first cluster or x4 is in first cluster and the remaining is in second cluster. So all these possibilities are there with us. So overall, like, how many ways do you think, like if we have 4 data point and we want to put this 4 data point into 2 clusters, then how many ways do you think we can, in how many ways can we do this? This is a like simple
2 to the
question.
power 4, 16.
2 to the power 4, right? So because we have 2 clusters with us, 2 box with us, let's say, and for the first box I have 4 choices, and for the second box I will have another 4 choices.
2 choices actually. Oh, 2 boxes we have, yeah.
Yeah, 2 boxes we have, and for each of the boxes I will have 4 choices, right? So basically I will have 2 to the power 4 choices in total, and this is assuming that some boxes can be empty, right? This is also counted over here. So just for a very small problem, like where I had a data set with 4 data point and we wanted to put it in 2 clusters. So just for the small data set, for a data set of size 4, I need, and the total number of possibilities I'm getting is 16, which is quite large, right? Now think of this n as maybe some 1000. We have, let's say, 1000 data point, and suppose still the number of clusters I want to put in the data set is 2. Then in that case, the total number of possibilities that we will have to put this data set into 2 clusters would be 2 to the power 1000, right? Which is quite large, right? And these are the possibilities that we have with us, correct? And from these many number of possibilities, what we have to do is we have to find the best possible clusters, right? This is what our goal is. Now, out of these 2 to the power 1000, for this example, I need one best possible case for clustering these data points in 2 clusters. So, okay. Any doubt so far?
Pretty clear.
Okay. So this is our problem. Now, when we say we want to find our best clusters among those among these number of 2 to the power 1000, we need the best clusters, right? So, all right. So, what is one metric that we could think of? So, let's say this is my cluster 1. This is my cluster 1 and this is my cluster 2. Now what we are saying is, though I have these many number of choices, like how can we determine which is the best, how do we determine like which data point to go into which clusters, right? So for that we need a metric to evaluate. And what we will try to see is, and this is quite intuitive also. Can anyone guess like how should we decide which data point to go where?
Yes, ma'am.
What do you think? What can be
F-
the metric that we
First,
can use?
yes, ma'am. First, initialization centroid, and second, assign cluster.
Initialization, centroid, and then assign clusters. Okay.
Yeah.
And then find the distance to the mean of the clusters. And if that is less than the distance to the mean of the cluster, the same cluster that the point is in, then we need to reassign to another cluster.
Yeah. So what you're telling me is algorithm. What I did ask is, like, if you have this problem, which metric can you use to uh, identify which data set should go in which cluster? So one very natural way to think of this is, can
We
you?
can group the like
Mm,
in the existing data. We can group the data first, and then in those, if we find that some data is, if a majority of data is similar, then we can have one cluster defined with that similarity criteria, and then as the algorithm goes on, it will find a suitable mean.
okay. Okay. So, see, the question, the thing here is that if you have the data sets with you, and if the data sets are assigned to these clusters, then what we want is that whatever the cluster mean you have for the first cluster, let's say for the first cluster, um, the mean is, let's say, mu of 1. And for the second, all the data points which are there in the second cluster, let's say the mean is mu2. Okay. So what we would want is, like, whatever data sets goes in, like whatever data set is in a particular cluster. So let's say in the first cluster, whatever data points you have, we would want this data set, all these data set, to be closest to the mean of this cluster, right? Instead of uh, so instead of being them closest to the mean of the second cluster. So in a sense, all the data points which are in this cluster, they should be as close as possible. I mean, the distance that each data point will have from its mean should be least. So this is the idea that we will extend to. So and what we want is that this distance should be as less as possible. So when you compute the mean of, I mean, the distance of each of the data point from its mean, we want that distance to be as less as possible. And same is for the second cluster, right? So we'll define a metric, and that metric, or that metric, let's say we call it as, we define it as a function. And this function that we give is denoted as capital F of Z1, Z2 up to Zn. This is in terms of when you have n data points. So we define this distance to be sum over distance which will denote it by, you can denote any distance metric you want, maybe L1 norm, L2 norm. So I'm just writing here with respect to L2 norm. So some like norm of xi minus mu of zi square, where I is varying from 1 to n. Okay. And what does mu zi mean? So whatever data point xi you have, if let's say if this data point xi is in, um, whichever cluster, that will be your ZI over here. Okay,
So mean of that cluster.
mean of that cluster, correct.
Ma'am,
So
so
which
Z1, Z2 are already existing in the cluster earlier. They are labeled already. So we
no,
already.
no, 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 they are not labeled. They are not labeled. So we have not yet started. What should we do? What we are saying is, let's assume that you have, this is just one example. Let's say that you have this data point with you, and once you have this data point in the cluster, what we would want is that the distance that you will get for it, the distance between these data points to this mean. So if the data point, let's say this is my xi. So if the xi is in cluster 1, I would want the distance of this xi from mu of 1, right? I will calculate this. Similarly, for every data point, I will calculate this distance, right? And I would want this distance, all the sum of all these distances, to be as less as possible. That is our goal. And even if I look at the second cluster, and let's say if this is my mean, I would want the distance of each of the point from its cluster mean to be as less as possible. So overall, the distance of each of the data point from the mean of that cluster should be as less as possible. That is the idea.
But ma'am, if there's the first data point, no, then the mean will be the same data point itself, correct? And then you add the second because there's nothing in the cluster.
There is nothing in the cluster. That will come to it later. We have not yet started like how should this be done. Yeah.
Okay.
So yeah. So what we are saying is that this is the function that we are interested in. This is our interest. This is our goal. So the goal is to minimize this distance. To minimize this f of z1, z2 up to zn. All right. We want to minimize this. Now, if I if I'm writing mu of zi like this, so sorry, what can we write mu of k as? So mu of k is what? Mu of k is basically the mean of that cluster, right? So the mean of that cluster will be given by, so whatever data point you have in that cluster divided by the total number of data point that you have in that cluster. So here K denotes the cluster indicator. I'm talking about which cluster, cluster K, let's say. So what is the mean of cluster K? So to find the mean of cluster K, I need all the data points which are in cluster K divided by the total number of points that I will have in the cluster K, right? So this can be written as, so I need the total number of points in cluster K. So this can be written as indicator function of Zi to be equal to K, where I is varying from 1 to n. And in the numerator, I want all the data points, so xi times the indicator function for Zi is equal to K, where I is varying from 1 to n. This is what my mu is. So all of you know what the indicator function is?
Yes, ma'am.
Yes,
It
ma'am.
indicates whether
Okay.
whether the data point lies in the kth cluster or not.
Whether the data point lies in the K cluster or not. Correct. So basically what it means is like if I talk about any general indicator function, so indicator function of whatever you have inside. Okay. So if I'm writing Zi is equal to K. So if Zi is equal to K, if it holds true, then it will be 1. And if it is not true, I mean Zi is not equal to K, then it will be 0. Okay? This is what it means by indicator function. Whatever here you have with you, if this holds true, you will assign it as value 1. Otherwise, you will assign it as value 0. So when we are writing this term, that indicator of Zi is equal to K, so I am basically taking only all those you will take only all those xi's which are in cluster K, because only for those data points you will have zi is equal to K. For rest, it will be 0, right? And same for here. Is this clear to all of you?
Yeah, it's clear. So
Okay.
in other words, the bottom part, the denominator is the counting thing. We are counting how many are in the cluster, and the numerator is adding up all the elements in the cluster.
Yes. So this is yeah. So this is my objective. My objective is to minimize this f of zi's. Okay. So now the question is, how can we do this? So my goal was to minimize sum over xi minus mu zi square, I varying from 1 to n, and you're minimizing for zi up to zn, right? So this is the question. So what it turns out is that we have too many possibilities for this. I mean, for like as we had seen earlier, that in general, if we have, let's say, n total of n data points, and k clusters, then I will need the total number of partitions would be k to the power n. And in case the data point is quite large, then this number goes quite up. So there are too many possibilities to partition this data set. And due to that, like solving this problem is a NP-hard problem, right? So there will not go like what NP-hard is, but you can think of it as this is not solvable in real time. You can think of it like that, that this cannot be solved. So what alternative method that is being provided to deal with this problem of NP hardness is the Lloyd's algorithm. Lloyd's algorithm, or this is also called the k-means algorithm. So what is done in the Lloyd's algorithm is that the very first step, so in Lloyd's algorithm, you have basically two steps. So the very first step is, okay, like before we go to the steps here, you should first initialize the data points. I mean, so by initializing, what we're saying is that initialize your z1 naught, z2 naught, so on till zn naught. So again, the setup is that we have n data point. So if we have n data point and we have k clusters, okay, so if we have n data point and k clusters, then each of the data point will be in one of these k clusters. So in the very first step, we'll do the initialization, and what we are saying is that you randomly initialize all these data point. That will call it the zeroth step, zeroth iteration. Let's say we call it a zeroth iteration. So in the very first step, in the initialization, you just randomly assign these values. So each of the data point you randomly assign, and they will definitely belong to this set 1 to k. Now, once you have randomly assigned, then the very first step that will come, the step 1 of the algorithm, is we will compute the mean of each of these cluster afterwards. So for every k at any thth iteration, so this is to denote the iteration. So any thth iteration, I will compute the mean of kth cluster at the thth iteration. And what this should be? This should be again sum over xi's, indicator of my zi for the tth iteration is equal to k, where I is varying from 1 to n, divided by sum over indicator of zi to the power t is equal to k. Okay, so this is what we are doing. Like we have what we have done is we have initialized. The very first was initialization. We have randomly initialized. Then once we have initialized, then what will happen is, since we have k cluster, let's take the example. Let's say I have 3 cluster. K is equal to 3. So if we have 3 clusters, then all these data points will go to one of these 3 clusters, right? So once you have the data points in these 3 clusters, you can compute the mean. Let's say if I talk about the first iteration. So in the first iteration now, each of these, like you can compute the mean. So I can compute mu1, I can compute mu2, and I can compute mu3, right? At any iteration, you will have this. And you will see the step 2 that you will have is the reassignment step. So in reassignment step, what is done is that for every data point, I will compute zit plus 1. And what zit plus 1 means? Zit plus 1 means like which, like my ith data point will go to which cluster in the t plus 1th iteration, right? So let's say in the first iteration, if I say that, let's say this is my xi, okay? So in the first iteration, my xi is in mu1. So where will this xi go to in the second iteration? Will it stay in the same cluster, or does it go to some different cluster, is what we have to see. And that is what is given by this zit plus 1. Okay, this is what we mean. So it's not that every data point goes to some different clusters in the next round. It is not possible. I mean, it may not be true that it always happens. So reassignment step, in reassignment step, what we are doing is that for every data point, I will check whether what is zit plus 1. That is, I would want to know that if the distance of, so argument, if the distance of my xi's with mu i's, right? So here mu zi at the tth iteration, this is what we will check. This is actually, so what it is saying is that you will do the reassignment only if one data point is more closer to the mean of its own cluster than the other cluster. For example, suppose this is my data point and this is my data point. I have, let's say, 2 clusters. These are the 2 clusters that I have. Okay. Suppose the mean of the first cluster is this data point. Or maybe, let's say this is the mean. And for the second cluster, let's say this is the mean. Okay. So now if we look at this, look at these cluster, I mean, if we look at all these data point, we can, from here, we can see that if for this data point, the distance for this data point from cluster 1 is lesser as compared to the mean of the second cluster, right? So this data point would want to go to cluster 1 in the next round. This is what we mean. So only if such situation is arising, then in that case only we will move our data points to the different cluster. Otherwise, we don't move. So these are the two steps is what is being done in the Lloyd's algorithm. And in case like you reach a situation where all the data points are closest to its own mean, then there is no reassignment. Then we don't reassign, and we can say that we have reached the algorithm has reached a convergence. Okay, so this is what we are doing in the Lloyd's algorithm.
So ma'am, initialize means assigning the mean, is it? What does initialize do?
Assigning okay, initialization means that every data point you are assigning to some cluster. So what we have written is Z1, Z2 up to Zn naught. This is what we have to initialize. It means, let's say I have x1, x2, x3, x4, x5. Let's say these are the data point, and I have k is equal to 2 clusters. So these data point, I need to initialize them. I mean, I will randomly initialize. So maybe I will say that x2 is here, x1 is here, x5 is here, and x4 is here, and x1 and x3 is here. This is the random, this is the initialization we're talking about. Okay.
Okay, thank you.
Okay. So in Lloyd's algorithm, these are the two steps that is being followed at every iteration. And in case you reach a point where no reassignment is happening, then they can say that the Lloyd algorithm has converged. Okay. So the solution that you will get from here, I mean, yeah.
Ma'am, I have one more question. So once we
Yes.
move, when we move and reassign, don't we have to recalculate the mean, or
Yes,
will
you
still
have to recalculate. You have to recalculate because this is for any iteration, right?
Yes,
So
yes, okay.
if that happens, then again you calculate again. I mean, this is happening in any iteration.
Yeah,
So
okay.
you compute the mean, and once you compute the mean, you check whether the distance of the data point from its mean is the smallest or not. So if there are some data points which is more closer to the mean of other cluster, then that point will be reassigned to that cluster. And when that happens, again, like there is a rearrangement, you can think of it. There are rearrangement in the data set in different clusters. And then again, I will compute the mean again. And then again, I will check this distance. And this will keep on happening, right? This will keep on repeating. And once you reach at a point when it is not, I mean, no reassignment is possible, then I can say I have reached the convergence. My algorithm has converged.
Okay, so when we reassign the mean, we restart from x1 only, correct? Or we have to start from x2?
Yeah, we start from x1.
Yeah.
We have to do it for all the data point.
Yes, yes, yes.
Yeah? Because the mean will keep changing, no? Once the reassignment has happened, the mean will update.
Yes, yes.
So if the mean has updated, you still have to calculate the distance from each data point to its mean. Okay.
Yes.
So okay. So once you have once the assignment has been done for this data point, then I can say that then I can say that this will be in a sense minimum, that this is the minimum distance you will have. So the solution that you will get, so what our solution was, f of, we had to calculate the value of this objective, right? And this value was sum over xi minus mu of zi whole square. So once the assignment is done, once we know where all these data point is finally going after this Lloyd's algorithm convergence, then we can find this value.
Excuse me, ma'am. One question. How do you
Yes.
determine the k? How many clusters?
How
to-
many clusters? Yeah,
Yeah.
so that is something where we will need the cross validation. And we have not looked at it yet. I mean, cross validation is something that we'll study only in week week 5, we not week 5, week 6. So that's just another topic, like how do you choose k is not, we are not going to learn it here. So that is like you have to run the code and see for which k is working better.
Okay.
So k is called the hyperparameter, and to choose k, you will have to do the cross validation. Okay.
Okay.
All right. So this is so once we have these assignment for each of the data point, I can compute this value. I can compute this objective, and the thing is that will this, whatever we get here, whatever value we get here, will this be minimum? Will be the least among all the k to the power n choices that we had? May not be. It may not give you the global minimum that we were looking for, but still it gives a reasonable solution to our problem, and
Local
that's why,
minimum.
yeah, it will give yeah, the local minimum maybe. It may not exist. Yeah.
It means there could be any other clustering, another type of clustering, which may be optimal.
Another type of clustering which may be
I mean,
optimal.
yeah, you said because there are k to the power n possibilities.
Yeah, correct. So
So
this, doing this, we're skipping a lot of steps, right? If you would have gone with k to the power n steps, I mean k to the power n possibilities, then that takes a lot of time, right? So to avoid that, we have this algorithm, and what we are saying is that this algorithm do converge to a solution. It may not converge to the global solution that we would expect for our original problem that we had, but still it gives a reasonable answer to this question. So this works well, and we have also done the proof of like how can we prove that there is a mathematical proof also done also, like why does the, how can we say that the Lloyd's algorithm converges? So that proof is also done. If you are interested, you can look into it at the proof. Yeah. So this is one result. The result is that Lloyd's algorithm can converges. So when we say that the Lloyd's algorithm converges, it means that at every iteration, the value of this function, the value of this objective at every iteration is every subsequent iteration should be decreasing, and that happens when you look at the proof. So what we are saying is that the value of f of z1 t plus 1 means I'm talking about the t plus 1 iteration, f of z1 t plus 1, z2 t plus 1, so on till zn t plus 1. This value would be always strictly lesser than is lesser than f of z1 at the tth iteration, z2 at the tth iteration, and zn at the tth iteration. Okay, and what can we say? This will be lesser than f of z1 at t minus 1th iteration, z2 of t minus 1th iteration, and so on. So this will keep on happening, right? So here, from here we can see that the objective function is strictly reducing at every subsequent iteration. So if it is reducing and there are so far only k to the power n possibilities that we can have, so at some point of time this partition will have to exhaust, right? So once it happens, we can say for sure that Lloyd's algorithm converges. So this is one reasoning that we can provide, that the objective function at every iteration is reducing. All right, so that was about the Lloyd's algorithm. Any questions so far?
Understood, ma'am. Clear.
Okay.
Ma'am explains once more time convergence.
Convergence. Okay, so I have not done the proof for the convergence, but I have just given the reasoning why the Lloyd's algorithm is converging. So what we are saying is that when you run this Lloyd's algorithm, then the objective function value that you get at every iteration keeps on reducing. It means if I talk about t plus 1th iteration, so the objective value at t plus 1th iteration will be strictly lesser than the objective value at tth iteration. Then if I talk about t minus 1th iteration, the objective value at t minus 1th iteration will be strictly lesser than the objective value which was at tth iteration. So this is the sequence that it is following, right? At every subsequent iteration, its value is strictly decreasing. And since we have only a total of k to the power n possibilities in overall we have only these many possibilities, which is finite, though it's a very large number, but it is finite. So, and if you see that if at every stage your value is decreasing, let's say first it was 100, went to 98, 95, 90, let's say 90, 19, let's say stays 90, 90, 90. Okay. So, but it is stopping somewhere, right? Because you have k to the power n to be finite. So it's a large value, but it's finite. So at some stage, it has to exhaust. And that's why we can say that this will converge, this Lloyd's algorithm will converge. Okay. All right. So next, the next topic that we will see is Voronoi regions. What is Voronoi region? So when we are doing the Lloyd's algorithm, what Lloyd's algorithm is trying to do is it's trying to find the best partition. It is trying to find different regions or different partitions that will give you the best cluster, right? So if it is just about let's say two clusters, so how should so now what we will focus on, like if we have different number of k's, let's say if k is equal to 2, k is equal to 3, and so on, how should my Voronoi regions will look like? So when we are saying Voronoi regions, it means that uh, I mean you are trying to find uh, I mean your Lloyd's algorithm is trying to find the best the partitions that will give you the best cluster, and those partitions is what we are calling it as the regions. Voronoi distance. Okay. So for example, if let's say I have two clusters, let's take the case of k is equal to 2. So when you have two clusters, then what will happen? Let's say oh, okay, let's say these two clusters we have, and this is my mu1 and this is my mu2. Now let's take some point in x1, c1, cluster 1. So if my point is in cluster 1, then according to the Lloyd's algorithm, the distance of xi, so the distance of x1, the distance of x1 from mu1 should be lesser than the distance of x1 from mu2, because we have run the Lloyd's algorithm, and the Lloyd's algorithm will give you such clusters where the data point in each cluster will be more closer to its own mean, right? So due to that reasoning, what we can say is that this should happen. The distance of x1 from mu1 should be lesser than the distance of x1 from mu2. So if that's the case, then my if I like solve it, so once I solve for this, what we should get is x transpose or x1 transpose of mu2 minus mu1 is less than equal to norm of mu2 square minus norm of mu1 square divided by 2 for every x1 belongs to, or let's maybe call it just x, that is better. Okay. So for every x in cluster 1, okay, this should happen. This is what we will get. So and if you look at this expression x transpose mu2 minus mu1, this is basically an hyperplane, equation of the hyperplane, right? So x transpose, you can think of it as some w less than equal to, this is some p. So this is the hyperplane that we get solving this equation.
It's a hyperplane.
Yeah, right. So how will this look like? And if I look at this figure, how should this look like? So what we get is that these I mean these Voronoi and this hyperplane will basically separate your data points into two regions. So if this is my mu1 and if this is my mu2, then how we find this Voronoi regions is we connect these two points, okay, and then take the perpendicular bisector. So take the perpendicular bisector. All right, this is the perpendicular bisector. So whatever is on this side of the hyperplane, these points will belong to cluster 2, and whatever point you have on the opposite side, this side, will belong to cluster 1. So in a way, your Lloyd algorithm is separating your data points into these two Voronoi regions, and this is giving us the best cluster. Okay, so this is the Voronoi region for when you have two clusters. Now what happens if you have three clusters? Okay, so if you have three clusters, we'll have three cluster means. I will have let's say mu1, mu2 and mu3. So this is mean of first cluster, this is mean of second cluster, mean of third cluster. And these cluster means have been obtained after running the Lloyd's algorithm. Okay. So whatever we did for the 2 k is equal to 2 case, we do the same thing here for the k is equal to 3 case. So we can connect, let's say I want to find the partition between mu1 and mu2. I connect these 2 points and I take its perpendicular bisector. So this is the line that I get for mu1 and mu2. Now, if I have to find for partition for mu2 and mu3, again I connect these two and take the perpendicular bisector. Similarly, for mu1 and mu3, I take its perpendicular bisector. Right? So these, this is what you are getting here, right? I mean, this line separating this one and this one. So whatever reason, so this, in this region, you will have all the data points which is in cluster 2. You will have all the data points in this region which will be in cluster 3, and in this region, you will have points which are in cluster 1. So this is what is happening. And these different regions that we have obtained, these regions are called the Voronoi regions. Okay. I hope that is clear. Okay.
Clear.
Yes, ma'am.
All right. So this was about the Voronoi regions. Now, like in case you have the data points which are, I mean, in case you have the data point which is not, I mean, your clusters are not, it cannot be represented in the form of line, then that's another class of clustering that will be called spectral clustering. We'll not discuss it for this class. I mean, it's not a part of your course. So, but that is also something which you can look into, and it's called spectral clustering. So if you are interested, you can look into spectral clustering. All right. So this was about the Voronoi regions. Now, next we will talk about the initialization. Initializations. So when we looked at the Lloyd's algorithm, the one kind of initialization that we gave is we randomly assign, in this starting, we randomly assign each data point to some clusters. So that was one way to do it. I mean, pick any k means randomly in a sense. So when we are randomly, like when we said we randomly assign this z1, z1 not, z2 not, so on till zn not, if we randomly assign it, so in that case, in a sense, we are saying we are randomly assigning the mean to all these clusters, right? So if you have k clusters and all the data points will go to any of one of these clusters, and each of these cluster will then have some mean with associated with it. You will have mu1, you will have mu2, and so on till mu k. So these means you have assigned it randomly. So any this is something that is done randomly. So this was one way to do it. But there is another way to do it, which is what we are going to look into now. And that way of initialization is called k-means plus plus. So k-means plus plus is an initialization technique. So in k-means plus plus, what we are doing is that instead of initializing each instead of initializing all these mu i's, we will only initialize one. We will choose any one mu. Okay, so we will choose, let's say, we'll choose mu1 not randomly. Choose mu1 not randomly.
If you choose randomly, does it have any drawback?
If we choose,
Randomly, then I mean, there is
no,
a
no, it's not a drawback. I mean, see, when we are choosing randomly, um, then in that case, the time, I will come to it. Let's first see this, like what are we doing over here? K-means plus plus. Then I'll come to the first one. So in K-means plus plus, what we do is we only choose one mean random. So we choose the first mean random from your data point, from your x1, x2, so on till xn. I choose my mu1 naught. So once I choose my mu1 naught, what I would still need is I would need mu2 naught, I would need mu3 naught, so on till I will need mu k naught. I will need those means, right? So the question is how to choose these means. So the very first we'll have to find mu2 naught, right? So for mu2 naught, what we are trying to do is we will choose. So if, let's say, if this is my data set and I have selected any one of them, let's say I have selected this as mu1 naught, this has been selected as mu1 naught, then the idea is that my mu2 naught should be chosen in such a way that it is as far from mu1 naught. Okay, that's the idea. We want to do that. So how can we, like, how do we then do mu2 naught? How do we find mu2 naught? So for L is equal to 2, which is mu2 for mu2 naught, I will compute the distance. I will compute the distance of each of the xi from mu1 naught. Okay, I will compute this distance, and whatever the minimum is, I will take this as score. So, okay, what we are going to do is we are going to define another term, and this is called score for a data point. Okay, so for every data point, we are going to assign a score to it. So let's say this is my x. So score of x would be, I will take min of j from 1 to so far till L minus 1. Norm of x minus mu j naught square. This is how we are defining a score. I'll come to it, what it means. So let's say so far we know only mu1. We only have mu1, right? So what happens? In that case, if we have only mu1 with us, then in that case, you will have min of j is equal to 1. Only 1 you have. Norm of x minus mu1 naught square. Okay. So this is going to be what? This is going to be just distance, since you have only z is equal to 1. This is just going to be distance of each of the data point from its mu1 naught, right? This is basically what it means, in case you only know mu1 naught. Because min here doesn't make sense. You only have one value inside. So we'll calculate the distance of each the data point from its mu1 naught, and that will be the score that is being assigned to each of the data point. So there will be some score associated with x1, some score will be associated to, let's say, x2, some score will be associated to x3, and so on. Now, once you have computed the score for each of this data point, then we will compute the distribution of these data point. Okay, so let's say I just take 5 example, maybe 5 data points. I talk about 5 data points. So I had x1, x2, x3, x4, x5. I have these 5 data points. Now, let's say the score of x1, let's say, and this I am trying to find mu2 naught. Okay, so let's say score of x1 I get to be a1. Score of x2 I get to be a2. Score of x3 we get to be a3. Score of x4 is a4, and score of x5 is, let's say, a5. These are scores that we obtain. Now you will have a probability distribution associated with each of these data point. So the probability distribution that you will have is, for the first data point, you will have the probability to be a1 divided by sum of these ai's, I is varying from 1 to 5. For x2, you will have a2 divided by sum over a2, right? So on. This is how the probabilities are being given for this data point. So what our goal was? Our goal was to select a mu2, select mu2 in such a way that it chooses the mu2 naught to be as far as possible in with respect to mu1 naught, and this has been done probabilistically, and this is it's not like that. If let's say it's not like whatever probability is the highest, that will be chosen, since it is you can think of it as like coin toss example. Like, we know that if it let's say it's a biased coin, and probability of head to be, let's say, 0.7, and probability of tail to be 0.3, right? So if I know these values, let's say this is what it is. Okay, if I toss a coin, can I say it for sure that you will get a head only?
No.
No,
No.
right? It is not possible that. Correct. So similarly, I mean, even though this coin was biased, still there is a chance that the tail can occur when you toss a coin. So think of it like that. So even though the scores, let's say, yeah, let's say the score is in this way. Let's say a1 is greater than a2 is greater than a3, a4, and a5. Though this is the score that is given, and based on that, the probabilities will also vary like that. Like a1 divided by sum over ai would be greater than all of this, right? So this is what is happening, but it is not. I mean, you can't say it for sure that the algorithm will choose this as the mu2 naught. Algorithm will choose my data point x1 as mu2 naught. You cannot say it for sure. It's probabilistic. It's not deterministic. It's a probabilistic thing, right? So this is what is happening here. So this is in this fashion, your mu2 naught is being chosen. Now let's say suppose that the algorithm chose x1 as my mu2 naught. Let's say it happened. Okay, so now what we are saying is, we know my mu1 naught, we know my mu2 naught. Now we need to know what should be mu3 naught, right? So if this is my mu1 naught, and if this is my mu2 naught that is being chosen by the algorithm, then ideally my mu3 naught should also be chosen in such a way that it is as far as possible from both of these, like from both mu1 naught and mu2 naught, right? That is the idea. I mean, this is what we should want, right? So again, for this, what we will do is we'll calculate this score for the data point. So score for the data point now will be what? Now you will have min over j is equal to 1 to 2 norm of x minus mu1 naught square, comma x minus mu2 naught square. Okay. This is how the score is being calculated. So for every data point, now you calculate this distance. So whatever is minimum, that will come as a score of x. And we do it for all the data point. And again, once you get the scores for all the data point, I know what will the probabilities for each of the data point to be chosen as the third cluster, right? So it is giving me some probabilities. And based on that, we'll know the probability distribution, and accordingly the algorithm will choose my mu3 naught, and so on. It will keep on happening.
So, ma'am, we have to eliminate x1 naught once we get the minimum, or we have to again include it,
Um,
because we'll keep getting the same value, no, ma'am?
which this one you're talking about?
Yeah, so once we get the score and then we get the probability, and it is selected at random, correct? Even though it is arranged in that minimal order, ascending order, right? So we get the mu2 naught. So whichever is the data point corresponding to mu2 naught should be eliminated, or it should still be kept to calculate mu3 naught.
Okay, see, this is what we're talking about is in terms of theory, right? But you don't, like, even though you calculate this, we don't know if x1 was actually chosen as the second cluster mean.
Yes.
Yeah. So these are what we're talking about is the theoretical aspect of this problem. But we still don't know if that was chosen.
Okay. Okay.
Yeah.
So we are just getting the means, right?
Yeah, we're just getting the means. So, like, what is the difference that is happening here is, like, it's not that k-means plus plus initialization is faster. I mean, this is just another way to like do the initialization. But when we did the random initialization in the very starting, that is actually more efficient as compared to
Yes.
this k-means plus plus.
Yeah, because the same data point can again get repeatedly selected, no, if you're not removing it.
Even in k-means, we are not removing it.
Yeah, even k-means even there we are performing it. But all this, I mean, once you do the code for this, no, you should be able to say it.
Okay, but I thought in k-means we are just assigning randomly data points to different clusters
No,
and
no.
then getting them.
See, this is just the initialization technique. Like once you in this when we talked about the Lloyd's algorithm in the starting, there you have like what we said is, one technique to initialize is to randomly assign our mu i's, right? Randomly assign my mu k, and their initialization is done. I mean, that is just one step. But here what is happening is, in the initialization, this is all the process that my algorithm is following. I only choose the first one at random. Then based on the probability that we get whatever probability distribution that we get for the all the data points, the algorithm is selecting one data point as mu2 naught. Then again, this is running, and it's taking more time to assign your mu k naught, right? And once you assign all this, like once this all is done, then at the end, the algorithm will give you mu1 naught, mu2 naught, so on till mu k naught. And this is being done in a probabilistic way. While, yeah, so this is being done in the probabilistic way. Now, once you have gotten your mu1, mu2 up to mu k, then you run your Lloyd's algorithm, and afterwards, everything is deterministic.
Okay.
Yeah, once this initialization is done, after this, it's all deterministic. Then you run the Lloyd's algorithm and find your answer.
Okay.
So, ma'am, could you just quickly go over this again? Try to do it quickly.
So k means plus plus is just another initialization technique. Okay. So in k means plus plus, what we are doing is we are only choosing the first cluster mean randomly. So we are choosing mu1 not randomly from a set of data point. So once we choose mu1 not randomly, then what is left to choose is all these mu2 not, mu3 not, and so on till mu k not. All this is left to choose. So what we are doing is that we would want, once we have mu1 not, we want to choose mu2 not, and ideally my mu2 not I should choose in such a way such that it is as far as possible from my mu1 not, right? This is the idea. This is how it should be. So this is one
I
benefit.
don't get this sentence, as far as possible.
Okay, so why it should be as far as possible? To get more clear clusters, you can think of it. So let's say this is my mu1 naught. I would want my mu2 naught to be far, right? I mean, so whatever the data point you have, I should choose, I mean, my mu2 naught should be in such a way that it is more far from mu1 naught. So that, like, all the data points that has to go to cluster 1, I mean, it's more
But the better separation will
the
happen.
better separation. Yeah, better separation will happen. You can think of it like that. So that's the idea that is being used here. So that is why we are calculating this scores. So, and scores is given by this formula. So once we compute the scores, we can find the distribution of the distances for this data point. And my algorithm, this is a probabilistic way. I mean, this k means plus plus is a probabilistic way to choose the cluster means. The algorithm is free to choose any data point as a second cluster, though, like, even if you have but it's like it will follow with a certain distribution. I mean, there is a high chance that a data point that has the highest score will get chosen as the second cluster mean. There's a high chance, right, as compared to the data point with the lowest score. So this is what is happening in k means plus plus.
So with the higher score, it will be chosen. I mean, it has higher chance to be chosen as the second mean. So, do you really, I mean, take it as second mean when you initialize?
No, I mean, this is a probability distribution we're talking about. No, I mean, even though a data point, let's say my data point xi has the highest score. So if it has the highest score, I mean, the probability with which this data point will be selected as the second cluster mean will be highest. But that does not imply that this data point will be selected as a second cluster mean. Right? Just like that, I gave the coin example. Let's say the probability of head was 0.7 and probability of tail
I got
was,
this part.
yeah.
But after calculating the scores, what do we do? I mean, do we make initialization based on the probabilities or what?
Based on the probabilities.
Okay.
Based on the probabilities.
We make the initializations.
Sorry?
We make the initialization.
Yeah, this is the initialization technique. Yes.
Okay. Got it.
And using this, you are getting all your remaining mu2 naught, mu3 naught till mu k naught. Once this is done, you perform your Lloyd's algorithm.
Got it. Thank you.
Yeah. Okay. So, okay, now what we are going to look at is like how should we choose the K? Someone had already asked in the starting, like how do we decide what K we should go for? So we wanted to minimize this function z1 to zn, which was which was norm of xi minus mu zi square. This is the function that we wanted to minimize. So I mean, when we take k to be equal to n, so number of cluster to be equal to number of data point, then what happens in this case? In this case, every data point becomes its own cluster center. So that distance becomes 0 and this distance becomes 0. But is that what we want? That is not is ideal, right? This is not ideal. This is not what we want. So k is equal to n is not a good choice for us, right? So we would want k to be smaller, right? We want k to be smaller. So what we have not seen this in very great detail. Like for to choose k, we'll use the cross validation, but we'll define we'll define a penalty function, and what our goal would be to we would want we would choose k star. I mean, our k star is the optimal number of clusters. K star would be arc of min arc of min over k, and this is your objective plus a penalty term that we define. So this is what we ideally do this. And there are different ways. We have not looked into detail. So
objective is the initial
objective is this
function that we talked about. Yeah.
Yes. Yeah.
And penalty is what?
Penalty is some penalty that we will give to some penalty that we will give in case my number of clusters are like if as the k increases, I would want to put some penalty to my objective, some function.
It is proportional to k.
Sorry.
Is it necessary that penalty will be proportional to the k size?
Penalty would be proportional to k size. No, penalty is a function. I'm saying it's a function.
So it is on to the user to decide what function they want to take.
It is some function of k. Some function of k is not discussed. I mean, we have not discussed it in great detail. There are different ways. So one, okay, so Ronak has put elbow method. Yes, elbow method is one way to choose the clusters in clustering. And then there are different, like there is something called Bayesian information criterion, archaic information criteria. There are things like that that is used to decide your number of clusters, and they have some different formulas, and we work on that and come up with an appropriate K. But that is not a part of this course right now.
So we don't have to understand that.
Not
So
yet. But
penalty is not something which is asked in the quizzes as well.
can you repeat? Penalty is not.
Like we are not going into the depth of penalty function, right?
No, not for clustering. No.
So like we have not discussed any relation like it increases with the increase in number of key or something like that.
We have discussed that. We have discussed that, and okay. So I'll tell you what. What is being discussed is, let's say you have your K. Okay. K is the number of clusters we're talking about, and this is the objective. And I know this is a convex, so okay. So sorry. So what we are saying is. For different K, so you have 1 2 3, let's go until K. Okay, so at each K you will have some objective value, and this will keep on increasing. This objective function value decreases with increase in K, and it will decrease when K reaches N, right? So how should it be? Maybe something like this. Okay, when K reaches N, I know my objective function value is 0, decreasing function. Now I will define a penalty for like it to reach at some ideal stage. I mean, what K should be chosen. So as the number of K increases, I will add this penalty function to my, I'll add this penalty function. Okay. So if that happens, when you take the addition of these two functions, you will have something like this. You will do something like this. And at whatever point, this objective plus penalty. So whatever K you reaches this to be the least is the K that my algorithm will select. Okay. That is what is being
Now
discussed.
it is clear. Thank you.
Sorry?
Yes. So if we ever have a question, we would be given the penalty or something.
Yes. Yeah. We have some tips to cover. Okay. Oh, who was there? Someone raised the hand. No, who was that? Let's see. Yeah. Anyone had anything to say? I saw the hand raise, but can't say it here.
It was a mistake, I guess, from that person's side.
Okay. Okay. All right. So this is what you have in the clustering. This is all you have for the clustering. I see. So some tips to cover all algorithm in ML. You can, I mean, not all can be covered in the course, but whatever algorithm has been done, just, you follow the lectures, and along with lectures, I would suggest also try to implement this in Python, and that will give you more clarity on what is happening.
Yeah, I'm trying to do that.
Yeah, that is a better way to learn ML. Okay, so that was all we had. Any questions?
No, ma'am.
Okay.
Ma'am, there is some k-medioids algorithm also. How is it different from the k-means plus?
I didn't hear your first part. What did you say? K
Medioids algorithm.
meteors.
Yeah.
Sorry, I have not heard about it.
No
I
problem.
yeah, I will check. You said meteoid.
Yes.
Okay, maybe I will just look into it. What it is?
Thank you, ma'am.
Yeah. Thank you, everyone.
Good night, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Good night.
Good night.
Thank you, ma'am.
Thank you.